Now we will talk about how to get to the virgin state, the demagnetized state that we have at zero field. So basically, if you remember, we talked about the normal induction curve, and the normal induction curve starts from this 0 point. So we have zero magnetization at zero magnetic field. But then when we go through the magnetization process, as you can see, the hysteresis loops show us that it's almost impossible to go back to this zero magnetization state, which is called the demagnetized state. That is actually not true. There are several methods to go back to this zero magnetization state or the demagnetized state. The first technique is called AC demagnetization, and so basically I'm talking about three well-known techniques. There are other techniques as well. So in the AC demagnetization process, what we do is we basically take advantage of these minor loops. So after completing the major loop here, so when we start tracing the loop again, we stop at an intermediate point and go back to in the reverse direction, so that we have a small decrease in the width of the hysteresis loop, and finally we go back to the zero state. So there is a demonstration of this in one of the videos that I have linked here, so I strongly suggest that you take a look at this video demonstration by Walter Levin. So basically the technique is the sample is, or the specimen is subject to a series of alternating fields of slowly decreasing amplitude. So in each cycle we have basically a decrease in the remnant magnetization that we observe, and as a result we find that eventually we will be going back to the zero magnetization state as the remnant magnetization will converge to zero magnetization. The second technique is thermal demagnetization. Now what we do is we basically try to break the exchange between the moments, so that the temperature is going to randomize these spins or the moments, and the way it's achieved is basically the sample is heated above the Curie point, so that we have a phase transition from a ferromagnet to a paramagnet. So it is heated above Curie point, and then we have to cool it down in zero magnetic field. In zero magnetic field, that is to make sure we're not re-establishing an orientation or realignment of the moments in the direction of the field. The third technique is basically mishandling, or we can say it's mechanical demagnetization. So you can just bang on it with a hammer, and eventually you will see that if you don't break the magnet, it will actually demagnetized by, for example, by dropping on the floor, it's mishandling, banging with a hammer, etc. So by mechanical means we can demagnetize the magnet and go back to this zero magnetization or approximately zero magnetization at zero magnetic field. Okay, so you will also see another demonstration of thermal demagnetization in the videos that I have linked to this one, so I strongly recommend that you watch another demonstration by Walter Levin for thermal demagnetization. And what I would like to do next is basically, before completing this discussion on basic concepts, I would like to summarize what we have learned and how to express them in CGS units and SI units. So the first one is has to do with the force between poles. The force between poles, magnetic poles, is expressed in SI units as F is equal to, if you have two poles P1 and P2, P1 P2 divided by R squared, where P1 and P2, the pole strengths are in unit pole strength, and R is in centimeters, and the force is in dynes. Now if I write this in SI units, the force between two poles written in SI units is mu 0 P1 P2 over 4 pi R squared, and this is given in newtons. P1 and P2 are in ampere meters, and R is in meters, and mu 0 is 4 pi 10 to minus 7 Henry per meter, for example. And if you want to do a conversion between forces, we can basically say that the conversion factor between a Newton and dyne is 1 Newton. 1 Newton is 10 to 5 dynes. So that's the conversion between these two. Now I'm going to look at the field due to a pole. So let's discuss the field, magnetic field created by a pole. So field of a pole. This is given, this is the H field. It's given as the pole strength P divided by R square. R in centimeters, P is in unit pole strength, and H is in given in Ersteds in CGS units. Now the same magnetic field created by a pole is 1 over 4 pi the pole strength P divided by R squared. It's given in ampere per meter. The pole strength was in ampere meter, so divided by meter square we get ampere per meter. And the conversion between ampere per meter and Ørsted is that 1 ampere per meter is 4 pi divided by 1000 Ørsted, or 1000 over 4 pi ampere per meter is 1 Ørsted. We can talk about magnetic induction, the B field. Magnetic induction. In CGS units, the magnetic induction B is magnetic field strength H plus 4 pi amp for most materials, and this is given in units of Gauss basically. So we have Gauss as the unit. Now in SI, B is equal to mu 0 H plus M magnetization, where H is in ampere per meter, M is in ampere per meter, and mu 0 is again 4 pi 10 to minus 7 Henry per meter. The answer is given in Tesla, and 1 Tesla, as we have seen, is 10 to 4 Gauss. And in CGS units, we have H in Ørsted, capital M magnetization is in EMU per centimeter cube, and B is in Gauss. Okay. The energy of a dipole in a magnetic field. Energy of a dipole. Its energy E is the dot product minus the dot product magnetic moment with H, and it's expressed in units of ergs. So magnetic moment is measured in electromagnetic units, H is in Ørsteds, remember. And in SI we can write this equation as E is equal to minus mu 0 m dot H, and the answer comes out in joules. The magnetic moment is ampere meter square. H is in ampere per meter. Mu 0 is again 4 pi 10 to minus 7 Henry per meter, for example. And the conversion between 1 joule and erg is 1 joule is equal to 10 to 7 ergs. Okay. We can talk about susceptibility. Susceptibility is basically the amount of magnetization we can get per magnetic field we apply. So it's M divided by H. In CGS units, it's going to be EMU per centimeter cube Ørsted. The susceptibility in SI is M over H, which is dimensionless because M and H are both in ampere per meter. And for permeability, we have permeability is mu, which is B over H, which is 1 plus 4 pi times susceptibility. So what is the unit of mu in CGS? Well, you can see that we have B in Gauss and H in Ørsted, so the unit would be Gauss divided by Ørsted, and the permeability in SI units, mu is equal to B over H. It is mu 0 times 1 plus susceptibility, so it has the unit of mu 0 because susceptibility was dimensionless. So this would be measured in Henry per meter. Now, one other thing I would like to mention is flux, magnetic flux. Flux phi is the dot product. So let's talk about the non-uniform flux, the dot product between H and the area vector. It's measured in Maxwell's. H is in Ørsted's, area is in centimeters square. The flux in SI is mu 0 integral H dot dA, and it's measured in Webers. And the conversion between Webers and Maxwell's is that 1 Weber is 10 to 8 Maxwell's. And for the magnetic moment, let's continue here with magnetic moment. Magnetic moment in CGS is basically the pole strength P multiplied by the distance between the two identical poles with the different signs, and it's measured in EMU. The magnetic moment in SI is the current I a current loop carries in an area A for a closed loop, and it's measured in ampere meter square. And the conversion between EMU and ampere meter square we talked about, but what is more important is magnetization. So this is something we should remember. Magnetization is magnetic moment per volume, which is measured in EMU per centimeter cube, and magnetization is magnetic moment per volume, which is measured in ampere per meter in SI, and 1 ampere per meter is 10 to minus 3 EMU per centimeter cube, or 1 EMU per centimeter cube is 1000 ampere per meter. Okay, so basically this summarizes what we have learned in the basic concepts part, and we have seen that we can express these equations in CGS and SI, but it's not just a unit conversion, it's basically a totally different view of a different way of looking at magnetism. So one is from the picture of poles, the other one is from the point of view of circulating currents. So in CGS units we're looking at the poles point of view, and in SI we're looking at the point of view of circulating currents. So we talked about demagnetization techniques, AC demagnetization, where the sample is subject to alternating fields with decreasing field strength, decreasing amplitude until we reach zero remnant magnetization. Thermal demagnetization, where the sample is heated above the Curie point so that it becomes a paramagnet and then cooled in zero field to lock the random orientation of moments. Mechanical demagnetization, it's by banging on it or dropping it on the floor through mechanical effects, we can demagnetize it. And then we have done an equation summary for force between poles. We have P1, P2 over R squared. P is in unit pole strength, R is in centimeters, force is in dynes. The force is in newtons in SI, it's mu0 over 4 pi. P1, P2 over R squared. P is in ampere meter, R is in meter, mu0 is 4 pi 10 to minus 700 per meter. The answer comes out in newtons, and 1 newton is 10 to 5 dynes. Field of a pole is pole strength divided by R squared. Unit pole strength per centimeter square is called Ørsted, and it is 1 over 4 pi P over R squared. For SI it's ampere per meter, and 1 ampere per meter is 4 pi over 1000 Ørsted. Magnetic induction is related to magnetic field H and magnetization with this linear relationship. B is equal to H plus 4 pi m in Gauss and mu0 H plus m in SI. So we express magnetic induction in Gauss in CGS and Tesla in SI, and 1 Tesla is 10 to 4 Gauss. Energy of a dipole is minus m dot h, which is found in Ergs. M is EMU, H is in Ørsted, and minus mu0 m dot h, or minus m dot b if you wish. That is in SI and measured in joules. 1 joule is 10 to 7 ergs. Susceptibility is dimensionless in SI. In CGS it's EMU per centimeter cube Ørsted. Permeability is Gauss per Ørsted in CGS, Henry per meter in SI because susceptibility is dimensionless. Flux is the integral H dot dA, the area vector. It's measured in Maxwell's in CGS, and Weber's in SI. It's mu0 H dot dA integral. 1 Weber is 10 to 8 Maxwell's. Magnetic moment is the pole strength. So if you consider a plus p and a minus p that are at a distance L from each other. So we define the magnetic moment to be the vector that points from minus p to plus p, and the distance between the two poles is L, and it's the pole strength P times L. That's measured in EMU. In SI, you have a current loop, that's the view of ampere, and you look at the area A and current I, and using the right hand rule you can find the direction of the magnetic moment. So it is you can see that it will be in the direction of the magnetic field this current creates. So using the right hand rule, if you curl your fingers in the direction of the current, your thumb points in the direction of the magnetic moment. Magnetic moment is in ampere meter square. Magnetization is in ampere per meter, and it's in EMU per centimeter cube in CGS, and you need a factor of 10 to minus 3 in order to go from EMU per centimeter cube to ampere per meter.